Pressure! The air around us is so strong that it can crush a railroad tank car. It's insane. So I'm super excited to talk about pressure. There's going to be a lot of things that you're going to learn, and we're going to go into it in detail. We're going to talk about it on a microscopic level. We're going to talk about how to create and read from a barometer, and we're going to get into like the crazy zoo of units, which I have some stuff that you will learn for. We'll describe standard temperature and pressure. Spoiler alert, there is no standard. And how to read a manometer as well. Okay, so what is pressure? Well, we all know what pressure feels like. If you've jumped in water, you feel the pressure of the water all around you. You've displaced the fluid and the water's like trying to get back into that space that you've displaced. It exerts a force that's perpendicular kind of everywhere throughout. So if you imagine now on a microscopic level, if you imagine this object coming, bombarding against a wall, it's going to exert a force over some contact area. And pressure, very simply, is the magnitude of that force divided by the magnitude of that area. That's kind of what pressure is. If we have a gas, then the pressure is this time average force against the container over time. We can increase the pressure if we increase the number of collisions per second. If we increase the impact speed, and if these two things are held constant, then if we decrease the surface area, that will increase the pressure as well. So this is our main equation, P equals F over A. How do we measure pressure? Well, way back in 1643, I remember it well, Evangelista Torricelli published his results on the barometer. He created the barometer, and what he did was he took this glass tube that was sealed on one end, he filled it with mercury, and then held the bottom so the mercury wouldn't fall out, probably not with gloves. And then he put the tube down into this container of mercury and removed his hand. The mercury didn't go down all the way. There is actually a vacuum as long as the tube was high enough. You see this vacuum here. For in static equilibrium, then the sum of the forces have to equal zero if you remember your physics. And since pressure is force over area, I don't think it's too big of a leap to say that the atmospheric pressure has to be equal to the pressure due to the mercury, the hydrostatic pressure. And it was found that at 0 degrees Celsius at sea level, the height of a mercury column was about 760 millimeters of mercury. So this was kind of used as the standard for a while, but there was problems with it. So Ostwald defined the standard atmosphere unit as equal to 760 millimeters of mercury. And I just want you to pause for a moment. I know you want to learn the material as fast as you can, but just think about this. This definition was 150 years ago, which is only a few generations. So only a few generations ago was a standard unit for pressure defined outside of this millimeters of mercury. And think about what we're doing now with our flying airplanes and AI and all this stuff. It's not that long ago where there's very fundamental concepts were just being learnt. The problem with using millimeters of mercury is that the height of a mercury column varies not only with pressure, but with temperature too. Things usually contract when they get colder, so the density goes up and the height is lower at lower temperatures than at higher temperatures. The standard atmosphere, attempts to account for that and kind of standardize against that, but a common thing to do is to convert everything into SI units, and that's what we'll do. Yes. Pressure is force over area, and this is the force due to gravity that's acting on the mercury inside the column. Using Newton's second law, F equals ma, and A is g right here. Now density is mass over volume, and if we solve for mass and substitute it in, this is what our force of gravity becomes. So it becomes rho times v, because mass, if we solve for mass, multiply both sides by v, mass is v times rho. So that's what we have right here, times g. And now we can substitute this into our force for pressure, where we have rho times volume times g over a. V is the volume of the mercury inside the tube. This tube is a cylinder, and the volume of the cylinder is the area times the height. So if we plug that in, we get rho times A times H times G over A. Well, check this out. A cancels out, and we're left with the pressure of the mercury in the column is the density times the height times G. This is the hydrostatic pressure. Okay, now we can plug things in. This is the density of mercury at 0 degrees Celsius. It's 595.1 kilograms per meters cubed. Now you can impress someone at a party with this. We could plug all this in. This is the density. This is the height of the Mercury column in meters. And then this is our gravitational constant G. So if we plug all of that in, we get 101,325 kilograms per meter second squared. This is the pressure in SI units, but we often merge them together to give us the Pascal, which is the derived SI unit. So that's 101,325 pascals. And nowadays, the standard atmosphere has been defined exactly as 101,325 pascals. 1 millimeter of mercury is defined as the pressure that, wait for it, 1 millimeter of mercury exerts. And that's this right here. This is the density of mercury at 0 degrees Celsius, the height times G. If we plug all the numbers in, this is the height in meters, and this is a gravitational constant density. If we plug all that in, then 1 millimeter of mercury has been defined as exactly 133.3 blah, 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 blah pascals. And in this way, millimeters of mercury is no longer defined as the height, as like literally millimeters of mercury in a barometer. It's defined against the Pascal, which I thought is kind of crazy, right? There's also the torr. And the torr also helps get around this changing heights based on temperature, but it's also like a head nod to Torricelli. And if you do the math, then almost exactly, not quite, but almost exactly 760 millimeters of mercury is equal to 1 standard atmosphere, 101,325 ATM. This brings us continuing on into our zoo of units. Pascal is the SI unit, although it has such a small magnitude that we often write it in terms of kilopascals. 1,000 kilopascals is 1 Pascal. And sometimes working with a big number or a prefix is a little inconvenient. So way back in 1949, the bar was created. It's a non-SI metric unit. 1 bar equals 100 kilopascals. Although nowadays, institutions are trying to depreciate both the bar and the standard atmosphere unit, although they are still widely used today throughout the world in many industries and probably will be for a very, very, very long time. This 1 bar, 100 kilopascals, it's equal to a little under 1 ATM and about 750 millimeters of mercury. Now, there's one other very common unit for pressure that you'll likely see, and that's the pound per square inch, PSI. 1 PSI is equal to 1 pound-foot over inches squared. What does that mean? Well, a pound-foot is the force of gravity on 1 pound. So the mass is 1 pound. This is gravity right here for F equals ma over inches squared. And to figure out what all this means, we'll convert things into SI units. So we'll plug in what G is in SI units, about 9.8 meters per second squared. We'll now convert the pounds and the inches squared. 1 kilogram is 2.2046 pounds, and 1 inch is 0.0254 meters. If we plug all these conversions in, pounds cancel out, the inches squares cancel out, and then one of these meters cancels out with, or this meter cancels out with one of these meters squared down here, and this gives us big number, 6,894.8 kilograms per meter second squared, but you might recognize these units as the Pascal, which is what 1 PSI equals. And if you do the conversions, it works out that 1 ATM is 14.70 PSI and 1 bar is 14.50 PSI. So this gives us our zoo of pressure units that's been historically brought along with baggage for the ride, but we still use all of these units throughout industry, and it's kind of good to have some familiarity with them. To convert between all of these units of pressure, it's just like converting with any other unit. You take the unit that you have, multiply it by a fraction with the unit that you want in the numerator, the unit that you want to cancel out in the denominator, and that gives you your desired unit. Now with STP is standard temperature and pressure. And big surprise here, standard temperature and pressure has no universal standard. It's usually defined as 101.325 kilopascals, which is 1 ATM for standard pressure, or 100 kilopascals, which is 1 bar. And temperature, standard temperature, is usually defined as 0 degrees Celsius, so 273.15 Kelvin. It's usually defined in this way, although it does vary based on the industry. Since your prof is an expert in whatever their industry is, just use whatever your prof uses and kind of go from there. I have a video going into detail, like deep diving into this STP and standardization and stuff like that. You can check it out if you want, but literally these are usually the values. Use what your prop uses. Okay, so we're going to go over some problems of measuring heights and calculating the pressures based off of barometers. And this is our first very popular exam problem right here. Calculate the height of a water barometer at 100 kilopascals, 20 degrees Celsius, and we're given the density of water right here. So we have this water barometer, and we want to know the height of the water in the column. Well, we're going to start off with our equation that we just derived. P equals rho hg. This is our pressure for the hydrostatic pressure. From here, we'll solve for h. We'll divide both sides by rho g, and then just flip the equation. And at this point, we can basically plug things in. We just want things in terms of SI units. So our density, 0.9972, is in grams per centimeters cubed. We want it in kilograms per meter cubed to be in SI units. So we'll multiply this by 1 kilogram for every 1,000 grams, so that grams cancel out. And then there's 100 centimeters for every 1 meter, although we need to cube this fraction because we have centimeters cubed that needs to cancel. And then if we kind of plug all this in, the density of water at this temperature is 997.2 kilograms per meter cubed. Okay, so we can basically plug all that in. This pressure, we're given it in 100 kilopascals, but we need to use the SI unit, the pascal. So we got to multiply it by 1,000. And then this is our density in SI units. This is our gravitational constant. And then this, we work through the math, it's 10.22 meters. So this means that if we had a water barometer just kind of out in the air, it would be over 10 meters high. Whoa! That's how strong atmospheric pressure is. Just a thing to note that we could have used kilopascals in the numerator as long as we used liters rather than meters cubed. It's a little tip. If you don't remember that, that's fine, but it's a bit of a shortcut that some students like to use. Okay, another super popular exam problem is this. We have the height of a mercury barometer at 25 degrees Celsius. It's say 813 millimeters. So this is our mercury barometer. We want to know what the height of the water barometer would be. So basically the height of the column if we were to switch the fluid from mercury to water. Since they're both under the same pressure, the pressure of the mercury has to be equal to the pressure of the water. And if we use our new favorite equation, P equals rho hg, we substitute that for each one. This is the mercury side, the density of mercury times the height of mercury times the gravitational constant equals the density of water times the height of water times g. And you'll check this out, g cancels out, and if we solve for the height of water, which is what we want, divide both sides by the density of water, we have this ratio, the density of mercury to water times the height of mercury. Now, at this point, we need to plug things in. We need to know what the density of mercury and water is at 25 degrees Celsius, because it varies based on the temperature. I looked up in the engineering toolbox you can see online, the density of water at 25 degrees Celsius is 0.997-ish grams per centimeters cubed. So we'll kind of plug that in there. And then if we look at the data tables, this is from the NIST website, the density of mercury at 25 degrees Celsius is about 13.5336 grams per centimeters cubed. So we can plug that into here. And at this point, we can just use grams per centimeters cubed because they cancel out. And this ratio, this fraction, becomes 13.57. It's unitless. The height of the mercury column is given. It's 813 millimeters. So if we plug all this in, this gives us a height of about 11,000 millimeters if the barometer was water. How high is that? Well, it's about 11 meters tall. So pretty high if it was water. While a barometer is useful in measuring atmospheric pressure, a manometer is useful in measuring other stuff, like gases and things like that. And there's two types. This is a closed-end type. The end right here is closed to the atmosphere. So the pressure of the gas pushes on the fluid, say mercury, and that pushes it up. And the pressure of the gas equals the hydrostatic pressure of the mercury. It's the pressure due to the force of gravity that's pulling down on the mercury, which is H rho, which is the density, times g. If you derive this, you can check that out, as opposed to the open end type. Now, if the gas has a pressure that's less than atmospheric pressure, what happens is that atmospheric pressure wins, it pushes down, and it pushes this column up such that the pressure of the gas plus the pressure due to mercury, or whatever the fluid is, equals atmospheric pressure. Now let's plug some numbers in to solve for the pressure of the gas. The pressure of mercury is equal to rho GH. You can check out my derivation if you need to see that. So at this point, we can just plug everything in. This is our atmospheric pressure, 1.010 atm. That's what we're given. And it's useful to have everything all in the same unit. So I'm going to convert everything into SI units. And the conversion for that for pressure is 101,325 pascals is equal to 1 atm. In this way, atm cancels out. And for the other one, we want it in pascals, right? And a pascal is a kilogram per meter second squared. So we got to be in SI units for the second term. Well, the density of mercury at this temperature, I guess it's not given, but just in this example, this is the density, is in kilograms per meters cubed times G times the height. And this is the height in meters, which is very important. So now that we're in kilograms, meters, and seconds and all that, that works out to be pascals. So we have this many pascals minus, or 15,604 pascals. The first term is to 4 sig figs because our atmospheric pressure is significant to the third decimal place. So we have 4 sig figs here. And then in the other one, we have 4 sig figs for the height. So we have 4 sig figs there. Now, if we subtract these two together, we have 86,730 pascals, which is actually 3 sig figs because we lose a leading place value right here when we subtract these two together, which is kind of neat. So if we convert to ATM, it's usually good to convert to the units that you're given in the question. So we'll convert that back, which works out to be 0.856 ATM. Okay, now we can have an open-end manometer where the gas has a pressure that's greater than atmospheric pressure. If that's the case, then it wins. It pushes down on the mercury column such that the pressure of the gas equals the atmospheric pressure plus the pressure due to the mercury, which is rho GH. So these are our 3 scenarios. The closed end, to get the pressure of the gas, it's simply rho GH of the mercury or whatever fluid in the column. If the pressure of the gas is less than atmospheric pressure, if it's an open end, then we got to take atmospheric pressure and subtract the pressure due to the mercury, rho GH. If the gas has a pressure that's greater than atmospheric pressure, it's an open end manometer, then we got to add rho GH to it to get the pressure of the gas. Great, and that's our manometers. So to summarize everything together, all of this information, pressure is the force per unit area on an object, and the pressure of a gas is that constant kind of time averaged force on the edge of the container. Pressure has a ton of units. You don't need to know all the units, just know that Pascal is the SI unit and know how to convert the other ones. Okay? This is very important when you're dealing with like ideal gases because the gas constant R has a slightly different value if you're in, say, units of bar versus units of ATM versus pascals or kilopascals or things like that. And then lastly, standard temperature and pressure has no universal standard, which kind of sucks. So just use what your prof uses because it's industry specific and your prof is an expert in whatever field they're in. So just use STP of their field in whatever course you're in there. Okay, so that's pressure and glad you went through it. Let me know if you learned anything, if it was helpful, and I'll see you in the next video. Cheers.